Okay, so we're going to work another problem now. This is a similar problem except going in the other direction. So we're now looking at really a cooling curve. So same kind of graph, except we're starting up at, um, sorry, this is 28 grams of water at 18 degrees Celsius. I forgot to write that down, at 18 degrees Celsius. So we're starting at 18 degrees Celsius up here, and we're cooling. And then once we reach 0, we have to go through a freezing phase till we get to ice, to pure ice at 0 degrees Celsius. So the same kind of thing as what we did with the last problem, except going in the opposite direction. Okay, and so again we have two basic steps. The first step is to cool the water off. So that's this region here of our curve. And then the next step is to freeze it. Okay. So these are the two things that we need to and this time we're not trying to figure out the time allotted here. We're just trying to figure out the total energy that's going to be released. Now remember, we're starting with a piece of ice. We're starting with a bit of water. So there's some water here, H2O liquid, and then we are cooling that to form a block of ice. So we can show this a little better maybe by putting it in a container, and there's some water in here. And then we're just going to cool that down till it forms a block of ice in here. So this is at 18 degrees Celsius, this is at 0 degrees Celsius, and we're going from H2O liquid to H2O solid. Remember that what's happening is our system is cooling down. That means it's releasing heat. So we expect Q for this entire process to be less than 0. Remember, when we have a system, that if the heat is leaving the system, that's going to have a negative sign, and if the heat is entering the system, we expect that to have a positive sign. Okay, so we want to just be careful and make sure that we have our sign convention right. Now what we're going to do is exactly the same thing. We're going to calculate how much heat is required to cool off first, and then how much heat is, not required, but released by cooling off, and how much is released by freezing. Okay, and so again, we're going to do this in units of moles. So we have molar heat capacity, and we have the enthalpy of fusion here. And these are given in units of moles per mole in each case. So we need to use units of moles for the water, which I've already done the conversion. 28 grams of water divided by the molar mass gives us 1.55 moles of water. So this is the number that we'll actually be working with, this set of moles. So the first thing we're going to do is cool. So we're going to cool the water off. Excuse me. And let's see what we have for this. So the equation for cooling is that the Q, the heat associated with this process, is going to be the number of moles times the molar heat capacity times the change in temperature. So the number of moles in this case is 1.55 moles of water. The molar heat capacity is 75.3 joules per mole Kelvin. Same exact thing as last time, but now the reason our sign is going to be different here, the reason we're going to end up with a sign less than 0 when we didn't before, is because our final temperature is actually less than our initial temperature. Remember, what we have is this delta T is always T final minus T initial. Well, what's the final temperature? 0. So our final temperature here is 0 degrees Celsius. Minus our initial temperature, which is 18 degrees Celsius. And so when we plug that in, what do we get? We get minus 18, we'll call it Kelvin. Again, it doesn't matter when you're talking about a delta T. Whether or not you call this Kelvin or degrees Celsius, it doesn't matter. It's only when you're talking about actual temperatures that they're different from each other. Changes in temperature are the same in both cases. So we plug this into our calculator, and what we get is minus 2100 joules, minus 2100 joules, or minus 2.1 kilojoules. Okay, let's not say let's minus 2100. Make this a little smaller. Minus 2100 joules, and that's the same thing as minus 2.1 kilojoules. Okay, so that's the first part. That's the energy associated with the cooling. Now, what about the energy associated with the freezing? So this is freezing. Well, the first thing to remember is that we have an equation, a chemical equation. It's actually an equation for a phase change, and it's that H2O liquid goes to form, not H2O liquid, H2O solid goes to form H2O liquid, and we have a delta H associated with that. It's called delta H of fusion, and this is equal to plus 6.01 kilojoules per mole. Now, what we want is actually the opposite. We want to go from the liquid phase to the solid phase. So remember, when we reverse an equation, what do we have to do with the enthalpy value? The enthalpy value changes sign. So when we actually want to do this calculation, we need to remember to include this negative sign. So let's do that. So the Q for this is going to be equal to the number of moles times, in this case, minus the enthalpy of fusion, because we are actually going the opposite direction. We're going from liquid to solid instead of solid to liquid. Okay, and so we can plug that into our calculator. Again, it's 1.55 moles times minus 6.01 kilojoules per mole. And the per mole and mole will cancel. And when we plug this into our calculator, we get minus 9.3 kilojoules. Minus 9.3 kilojoules. Therefore, our total energy released, the total energy released as heat, is the minus 2.1 kilojoules required to cool off the ice, and the minus 9.3 kilojoules required to freeze the ice. Minus 2.1 to cool the water, and minus 9.3 to form the ice. Okay, and so our total Q here, the total amount removed as heat, is equal to minus 2.1 kilojoules plus minus 9.3 kilojoules, and that's minus 11.4 kilojoules. So hopefully you kind of get a flavor now for how to do any of these problems. When you draw your curve, you look and see what's happening with the curve. And if it's in a region where the curve is moving up and down like this, where the temperature is changing, you have these kinds of equations, either involving mass and specific heat, or number of moles and molar heat capacities. And then in these regions where it's flat, you're going to have some kind of enthalpy. It'll be an enthalpy of vaporization, or an enthalpy of fusion, or an enthalpy of sublimation, or something like that. And you will have to use the number of moles of your substance multiplied by this, making sure to pay attention in which direction you're going so that you know the correct sign, you know which sign you need to use. And that will give you the total energy change associated, the total enthalpy change associated with that phase change process. And this will allow you to calculate the total enthalpy change for any process, whether it be just a heating or cooling process, or a phase change process, or a combination of those different kinds of processes.